Okay, we continue with this explanation of figures from this chapter, memory. So this next figure, 24.10, is showing, again with monkeys, single unit recording study. In this case, monkeys have to look at the center of the screen, what's called fixation point, and a target will appear anywhere on the screen. Then the target disappears. It is flash. It appears very fast on the monitor, and then after it disappears, the monkey has to keep on looking at the center of the screen as long as the experimenter wants. And when the fixation points disappear, the monkey has to make a saccade, has to look at the place where the stimulus was presented. So that the figure A, and the delay period is showing a square that will represent the monkey working memory. Let's say it's he's remembering the stimulus is there. It's not there anymore, but he's remembering. And then when the fixation disappears, he looks at the place where the stimulus was. And down there we have the single unit activity again from that neuron. In this case, it is showing activity from the interparietal neurons, not frontal neurons. So those neurons begin firing when the target is presented and continue firing through the delay period until the fixation point. Until the fixation point disappears. This next image, it's actually not so hard to understand. It's a theoretical postulation from Hevs, Donald Hevs, and he was trying to explain here his hypothesis about how memories are created. So when you perceive a stimulus, your neurons activate, and if you perceive the stimulus long enough or with enough strength, those neurons, activated neurons, will create connections between them, and then you have a modification and strengthening of those circuits in a way that when you perceive the stimulus again, or when you perceive part of the stimulus, that memory of the stimulus, that engram, will be activated again. And the interesting thing about this hypothesis is that memories, in this way, memories are created based on perception. So the same pathway they go when you perceive something is the same pathway that is activated when you remember something. This was demonstrated later, and so this is it was demonstrated to be true that the same pattern that it's activated when you perceive something is also activated when you remember something. This next image is showing a very important brain region related to memory, to declarative memory, and that region is called the hippocampus. You can see in here it is in the medial temporal lobe, and during a long time researchers didn't believe there was a specific brain region in the cerebrum. They believe many brain regions were equally necessary to create memories and storage memory. But after a specific brain case, we will see later, specific brain surgery performed to a person, we know now that this medial temporal cortex, and mostly the inner part of that cortex called the hippocampus, entorhinal cortex, perirhinal cortex, and parahippocampal cortex, those regions are very important to create new declarative memories and storage and remember. So this is the way, the pathway it follows. Sensory information goes to cortical association areas, those complex areas, not the areas recruited for perception, but the areas more related to concepts or complex concepts. And then the parahippocampal and rhinal cortices, hippocampus, and through the fornix, which is axons. Information also is shared with the thalamus and hypothalamus, the encephalon. And then again, after the hippocampus, information goes back to cortical association areas, which means that perhaps memories are storage in cortical association areas, in the same areas that were activated when you perceived stimulus in the first place. But in order to be stored and remembered, they have to go through this parahippocampal, rhinal, and hippocampus pathway. If they do not follow this pathway, they will never be storage and remember later. This is also single unit recording studies with humans. In this case, human subjects are people who has disease, mostly epilepsy, and they need to have surgery. So they put in electrodes in their brains, and was this researcher found, this is an Argentinian researcher called Rodrigo Quianquiroga. He found that some neurons in the temporal cortex respond to concepts. How does he know this? Well, he showed images of, for example, one actress, Halle Berry, and the neuron in this patient responds strongly to the face of Halle Berry, but not only to her face, but also to her face mask, for example, with sunglasses, or with a mask in one of her movies, or also a black and white figure of her, and also her name written on the screen. So the same neuron fired a different modification of this concept, means that the neuron is not firing to an image but to a specific concept. They call this concept cells. I'll also give you the paper, this paper, because it's very interesting to read. And we got finally here, this is one of the most important and paradigmatic cases in the history of neuroscience. Patient HM. This person was he had epileptic seizures, very strong ones, and they did some surgery. They removed bilaterally both inner parts of the temporal lobes. You can see in the images which parts of the brain were removed, and as a result, HM was unable to remember new things. He had what we referred before as anterograde amnesia, and he was never able to remember anything new after the surgery, even 50 years later. I mean, he died at the age of 82 in 2008, and this was a very important case because it showed us that there is a specific brain region related to memory, storage, and also to remember, retrieval. And because even though he wasn't able to remember new declarative memories, he couldn't remember who a person was or what was he doing last week. Anyway, he was able to remember some other kinds of memories, which we now call non-declarative memory. And this is important because it tells us that those two memories requires different pathways, different brain regions to be created and to be remembered. Then we came to this figure finally. This is a delay non-matched to sample task. In this case, the monkey is shown one stimulus, for example this red circle, and then after a delay period he is presented with two stimulus, and he has to choose the one different from the one that was presented before. That's why it's called non-match to sample task. And this figure shows the effects of medial temporal lesions on this task. So if you make a lesion on the temporal lobe, the area we know it's important for memory, then the monkeys start performing worse. And if the delay goes more, you increase the delay up to 2 to 10 minutes, then the performance is even worse. Okay, and in here you can see all the structures. This belongs actually to a box called the Korsakoff syndrome and the case of NA. This is important because we were talking about hippocampus and some medial temporal lobe regions, parahippocampus cortex, etc., related to memory. But I don't know if you remember, there was one figure before, I'll show it very fast. This one, it shows that through the fornix you have connections with the thalamus and hypothalamus, and this is what is shown in here. The fornix, it's the color green, and you can see a purple color showing the mammillary body. That is actually hypothalamus structures. And this shows a very strong connection between memory-related brain structures and in the temporal cortex, and memory-related brain structures in the thalamus, in the diencephalon. Because some people with damage in some diencephalon regions, like the mammillary body, also showed impairments in memory very similar to the one we show in the case HM. Okay, so we will stop in this slide and we'll continue in the third and last video.